This program was produced by the Maryland State Department of Education, Division of Instructional Television.
Many common, everyday problems are of a mathematical nature and can be illustrated by a mathematical model.
For example, recently I was in a post office looking over the parcel post rate schedule. I noticed that the cost of sending a package depends on two things. First of all, to the zone to which it is being sent. And secondly, within a specified zone, the cost of sending a package depends on the weight of the package.
So with this in mind, let's look in on a situation which possibly might occur in a typical U.S. post office with Bob and Ray.
Weighing parcels.
Well, there's no problem there, Lou. I've weighed a few packages in my day, you know.
Well, we like to think of them as parcels, not packages, Ed. Now, we use these two for our trainees. I'll be demonstrating with this one, and you'll be using the other.
Okay.
We use the four-step process. You weigh it, you zone it, you cost it, and you send it. We call these steps the Big Four.
Huh.
It's a little nickname I dreamt up for the process.
Right. I see you using a Hercules weigher there, huh?
Not a weigherhead. No. We like to think of these as scales.
Scales.
Right.
Check. I got you.
Now, this parcel weighs, 1 pound, 15 ounces. For training purposes, we'll assume that this is going to Chicago, which would be Zone 4, and that completes our second step.
Check. I'm right with you, Lou. I see you using a U.S. Postal Service rate scale card here, too, huh?
That's right. Now, it gives me the postage cost, see? 75 cents for 1 pound, not exceeding 2. 85 cents for 2 pounds, not exceeding 3, and so forth.
Right.
With experience, you'll get out of that, too.
Sure.
Now, this parcel needs 75 cents postage, see? Then, we put the parcel in the sack. That completes the process. Hey?
That's an Australian muslin bag there you use, isn't it?
Only quality materials are used here, Ed. Incidentally, we call them sacks.
Sacks.
No,
right.
not bags. Now, why don't you try this same size parcel yourself?
Okay.
Same thing as the other parcels.
All right. Well, in that case, it would be the same postage, wouldn't it?
Oh, not necessarily. Now, that's a little challenge we like to sneak in on the trainees at this point, Ed. No. Hey.
2 pounds, 1 ounce.
Right. And it's going to Chicago, right?
Right. So that's Zone 4.
Right.
So that would be 85 cents, 10 cents more than your package.
Right. Now, my parcel was, 1 pound, 15 ounces, and yours 2 pounds, 1 ounce. That's
Right.
a 2 ounce difference, putting your parcel at a different rate on the rate scale, see?
Right. You're quick, Lou. You got a real good mind for mathematics.
Well, I like to think so. You know, I majored in weights and scales in school.
Oh, really?
Yeah. Any questions, Ed?
Yeah, just one. At what step do you put the stamps on the packages?
Parcels.
Parcels, I mean.
Stamps on the package.
What step is
what
that?
Step? Hey, I'll have to call a meeting. How could I have missed that?
I didn't mean to throw a monkey wrench into your lecture.
Well, there goes the Big Four, just like that.
Maybe you could call it the Big Five or something.
Ed, I'd like to talk to you privately. Now, don't let this get around you.
You know, Rich, that situation of Bob and Ray's would be interesting to consider as an example today.
It sure would, because there would be discontinuities in the graph of the parcel post rate schedule.
It does seem unreasonable to charge more postage for a package that may weigh only an ounce more than another. But that's the way the postal rates are figured. There must be a cutoff point somewhere.
This is true, and it does make an interesting function, especially when we look at its graph. Notice it progresses in jumps. The value of the function is 75 cents for values of the domain from 1 to 2 pounds, including 1, excluding 2. 85 cents for 2 pounds to 3 pounds, and 95 cents for 3 pounds to 4 pounds. Note the solid dot on the left side of the weight scale and the open dot on the right side. Each of these jumps is a point of discontinuity of the function.
This is one example of a step function. Another example of a step function is the greatest integer function, a concept we'll discuss later on today.
Last time, we defined the concept of continuity by using what might be called the triple test definition. Remember that a single statement in this definition led to three conditions which must be met for a function to exhibit continuity at a point. The basic definition stated that a function f defined in some neighborhood of a is continuous at a if the limit of f of x as x approaches a equals f at a for all x belonging to the domain of f. This is equivalent to the following three conditions. Number one, the limit of f of x as x approaches a exists. Number two, f at a is defined. And number three, the limit of f of x as x approaches a equals f at a.
In Lesson 5, we introduced a formal definition of limit in terms of delta and epsilon. We can use that definition here in order to make precise the first expression, that is, the limit of f at x as x approaches a exists. For the moment, we could let cap L represent the number that exists and equals this limit. So using the delta epsilon definition of limit, we can say the limit as x approaches a of f at x is equal to L if and only if, for all positive epsilon, there exists a positive delta, such that the absolute value of f at x minus L is less than epsilon whenever the absolute value of x minus a is greater than 0 and less than delta, remembering that x must belong to the domain of the function f.
Remember, in defining the limit concept, we pointed out that we didn't care whether or not our function was even defined at the limiting point a. This was why we placed the condition, the absolute value of x minus a greater than 0. This means that x cannot be equal to a.
That's right, Rich. We simply ignored the whole question of the function f at the point x equal a when we discussed the limit of f as x approached a.
Right.
But our definition of continuity requires that f be defined at a. This means that we do not exclude a. It means that x must be able to take on the value of a. Thus, we only need to choose x's such that the absolute value of x minus a is less than delta, and we can omit the restriction greater than 0.
Furthermore, the definition of continuity requires that the limit of f of x as x approaches a is the value of the function at a. Thus, we can define continuity of a function f at a point x equals a using suitable modifications of the limit definition. Namely, f is continuous at x equals a. If and only if, for all positive epsilon, there exists a positive delta, such that the absolute value of f at x minus f at a is less than epsilon whenever the absolute value of x minus a is less than delta, and x is an element of the domain of the function f. Notice we have made basically two modifications in the limit definition in order to have the definition of a continuous function presented here for you. First, f at a in the second line has replaced L. And secondly, we have now omitted the restriction, the absolute value of x minus a greater than 0, since x may equal a. Examining the graph of a continuous function, we can again see how this delta epsilon definition of continuity works.
Call this function the f function. We are to examine it for continuity at a. The function has value f at a for x equal to a. By the delta epsilon definition, we choose an epsilon and form a neighborhood, epsilon units above and below f at a. If, for any such epsilon, we can find a delta such that any x within delta units of a maps into a value within epsilon units of f at a, and note this includes a itself, then the function is continuous at a.
Another way to discuss continuity is to examine a function that fails to be continuous at one or more points. Now, here's a nice one. It is the greatest integer function. Note the bracket notation, which indicates the greatest integer function. It is defined for all real numbers. For any real number x, the value of the greatest integer function is the largest integer equal to or less than x. For example, f at 3.7 equals the largest integer equal to or less than 3.7, that is 3. F at negative 2 equals simply negative 2. And f at negative 4.5 equals negative 5.
Let's examine the graph of the greatest integer function and apply the delta epsilon definition for continuity at one of the jumps. Here's the graph. Note, for example, f at 0 equals 0, f at 2.5 equals 2, f at negative 1.5 equals negative 2. Let's ask, is the greatest integer in x continuous at x equal to 2? Intuitively, it is not. But let's see if that can be proven. We know that the f at 2 is equal to the greatest integer in 2 is equal to 2. Also, f at x is continuous at x equal to 2 if and only if, for all positive epsilon, there exists a positive delta, such that the absolute value of f at x minus f at 2 is less than epsilon when the absolute value of x minus 2 is less than delta and x belongs to the domain of the function f. Suppose we try a specific value of epsilon and then see if a value for delta can be found. Suppose we try epsilon, say, equal to 1/4. If x lies slightly to the left of 2, suppose it's in the interval from 2 minus a half, that's 1.5, to 2, then the greatest integer in x is equal to 1. This is true, in fact, for any value to the left of 2 down to 1. For instance, the greatest integer in 1 7/8 is equal to 1. F at 1.5 is equal to 1. F at 1 1/16 is equal to 1. And the absolute value of the greatest integer in x minus 2 is equal to 1. But 1 is not less than 1/4. So the greatest integer in x minus 2, the absolute value of the greatest integer in x minus 2, is equal to 1. But that's not less than 1/4, which is our value for epsilon. Now suppose x lies between 0 and 1. The greatest integer in x is equal to 0. For example, the greatest integer in 15/16 is equal to 0. F at 3/8 is equal to 0. If that is the case, the absolute value of the greatest integer in x minus 2 is equal to 2, and that's not less than 1/4. In fact, the situation deteriorates as x gets smaller and smaller. So we cannot have the absolute value of the greatest integer in x minus 2 less than epsilon. That is, the absolute value of f at x minus 2 is not less than epsilon for all x's in any delta neighborhood of a. Therefore, the greatest integer in x is discontinuous at x equal to 2.
What this means is that there are really two kinds of continuity. First of all, continuity at a point, local continuity, and secondly, continuity over an interval, global continuity.
The greatest integer function is discontinuous at 1 and indeed at every integer. It is, however, continuous at all other points, and this illustrates for us nicely the fact that continuity is a local property.
A function may be continuous at some points of its domain and discontinuous at others. We are chiefly interested in functions that are defined on intervals. Furthermore, we say a function is continuous on an interval if it is continuous at every point of the interval.
At every point of the interval except possibly for the endpoints.
Right. The greatest integer function is continuous over the open intervals 1 to 2, 2 to 3, 3, 4, and so on, but discontinuous at each integer.
Two things should be noted here. First, if a curve is discontinuous at a point, it would be said to be discontinuous over any interval containing that point. Secondly, if a curve is continuous at every point of an interval, except possibly for the endpoints, then that curve is said to be continuous on that interval.
In Lesson 7, we proved that the limit of a sum is equal to the sum of the limits. Just a few minutes ago, we pointed out the differences between the delta epsilon definitions of limit and of continuity. We noted that these definitions were very similar, and that if we start with the definition of a limit at A and let cap L equal f at A, and if we remove the restriction about a deleted neighborhood of A, then we get the definition of continuity at A.
Let's hypothesize several continuity theorems and at the same time contrast them with their corresponding limit theorems. And then in a moment we'll approve at least one of the continuity theorems. First limit theorem, the limit of a sum equals the sum of the limits, if the limits exist, of course. Similarly, if f at x and g at x are continuous at x equals c, then the function defined by adding f at x and g at x is also continuous at x equals c. Next, recall that the limit of a constant times a function is equal to the constant times the limit of the function, both limits as x approaches a, for k, the constant, belonging to the set of real numbers. This one can be proven by the use of the definition of limit. Then, if f is continuous at x equals c, we postulate that the function defined by k times f at x will also be continuous at x equals c. So the product of a real constant and a continuous function yields a function which is also continuous at the same point under consideration. Next, the limit of a product. This has been proven to be the product of the limits as x approaches a for each function. On the other hand, if f at x and g at x are continuous at x equals c, then their product, f at x times g at x, will also be continuous at x equals c. Now let's contrast the theorems for the limit of the quotient of two functions and continuity of the quotient of two functions. When we discussed the limit of a quotient, f at x divided by g at x, we stated that if the limit of g at x is not equal to 0 as x approaches a, and if g at x is not equal to 0 for x's in some deleted neighborhood of a, then the limit of the quotient equals the quotient of the limits. That is, the limit as x approaches a of f at x divided by g at x is equal to the limit of f at x divided by the limit of g at x, both as x approaches a. Likewise, if f at x and g at x are continuous functions at x equals c, and if g at x is not equal to 0 for all x's in some neighborhood of c, then the quotient, f at x divided by g at x, is also continuous at x equal to c. Therefore, sums, differences, products, and quotients of continuous functions are also continuous on their respective domains. The proofs follow directly from the corresponding theorems about limits.
As an illustration of the sort of reasoning used in proving continuity theorems, let's prove one of these rigorously. Suppose we work with the sum of continuous functions and allow it to serve as a guide for the other continuity theorems. If f at x and g at x are both continuous at x equals c, then the sum is continuous at x equals c. Well, here is what we must show. For all positive epsilon, there exists a positive delta, such that the absolute value of the difference between f at x plus g at x and f at c plus g at c is less than epsilon. Less than epsilon whenever the absolute value of x minus c is less than delta, and x is an element of the domain of f plus g. We begin our proof by assuming some positive epsilon is given. By hypothesis, both f and g are continuous at x equals c. Hence, f at x is continuous at x equals c if and only if, for all positive epsilon, and here we choose epsilon to be 1/2 the value of the epsilon given above, epsilon divided by 2 greater than 0, there exists a delta sub 1 greater than 0, that is positive, such that the absolute value of f at x minus f at c is less than epsilon divided by 2 whenever the absolute value of x minus c is less than delta sub 1. Notice that we use epsilon divided by 2 as we did in the proof of the limit of a sum. The definition calls for any epsilon, so we choose epsilon divided by 2, 1/2 of the epsilon chosen for the sum of f and g. The fact that g is also given to be continuous at x equals c allows us to apply the definition of continuity again. Note the use of delta sub 2 in the application of the definition this time.
Note we have used delta sub 1 and delta sub 2 in these statements about continuity for f at x and g at x. This is because of the fact that the two deltas could have different values. As with the proof in Lesson 7, when we proved that the limit of a sum is equal to the sum of the limits, we again make the same two important assumptions. First, the domain of f plus g is the intersection of the domains of f and g. And second, let delta be the smaller of delta sub 1 and delta sub 2. Note the use of the minimum notation.
Now we can return to the expression given by the absolute difference, the absolute value of the difference of the sums. We are going to show this to be less than epsilon whenever c is within delta units of x in order to prove that the sum of two continuous functions is also continuous. Using some elementary properties of algebra, we know that this expression equals this, simply by some regrouping. And then using the triangle inequality, and this you should recall in its general form as the absolute value of a plus b less than or equal to the absolute value of a plus the absolute value of b. So our original absolute value is less than or equal to this sum of these two absolute values. Absolute value of f at x minus f at c plus the absolute value of g at x minus g at c. You should also recall from our assumption about the continuity of f at x and g at x, and what we were given there, that the absolute value of f at x minus f at c is less than epsilon divided by 2, and the absolute value of g at x minus g at c is also less than epsilon divided by 2. So we may write the absolute value f at x minus f at c plus the absolute value of g at x minus g at c is less than epsilon divided by 2 plus epsilon divided by 2, or simply epsilon. If we assemble all of our statements, we have for any positive epsilon the absolute value for f at x plus g at x minus the quantity f at c plus g at c less than epsilon whenever the absolute value of x minus c is less than delta, which is equal to the lesser of delta sub 1 and delta sub 2.
Thus, the sum of two continuous functions is also a continuous function.
In our discussion of continuity, we saw that the limit of f at x equals f at a as x approaches a means that for any positive epsilon, there exists some positive delta, such that whenever x is an element of the domain of f and the absolute value of x minus a is less than delta, then the absolute value of f at x minus f at a is less than epsilon. Notice the value of delta depends upon the value of epsilon that has been arbitrarily chosen. And and this is very important to the concept that we wish to discuss now, on the value of A. That is, a particular point of the domain.
The choice we will make for delta may vary considerably for different choices of a value A in the interval under consideration.
As an example, let us consider the function y equals f at x equals 1 divided by x in the open interval, say from 0 to 3. Notice that the function is continuous at every point of the interval, but it becomes increasingly steeper near the left-hand side.
Let's consider a portion of the curve here at x equal a and examine more closely the restrictions placed upon delta by epsilon and a. If we choose a value for epsilon, then we have an epsilon band determined by the lines y equals f at a plus epsilon and y equals f at a minus epsilon. The projection of the intersections of these lines and the curve onto the x-axis yields delta sub 1 and delta sub 2. That is, a minus delta sub 1 and a plus delta sub 2.
Yes, but usually we are concerned about the smaller of these two in order to have a symmetrical neighborhood, so we would choose delta sub 1 here. Clearly, I believe that we can see that when the curve is fairly level, as at the right here, a relatively large value for delta can be used for a given epsilon.
Here we're talking about the value x equal a. Let's consider a portion where the curve is becoming more steep, say at x equal b.
We keep the same value for epsilon as when we were considering x equal a. This gives us an epsilon band of the same width as before. But note now the intersection of the curve with the lines y equals f at b plus epsilon and f at b minus epsilon. The projection of those intersections onto the x-axis gives values for delta sub 1 and delta sub 2, which are much smaller than before.
This means that there is no unique value for delta, and that delta depends not only upon the value of epsilon that is chosen, but also on the value of the limit point, a or b, that is chosen on the x-axis.
Some functions are better behaved than the function 1 divided by x. They have the property that not only are they continuous on some interval, but for any positive epsilon, there is a positive delta, such that the definition holds, and where delta does not depend upon a, but only on epsilon. That is, for any given epsilon, there is a single value of delta that will work for every value of a in the interval. Such functions are said to be uniformly continuous on the interval. Keep in mind that simple continuity is a property of a function at a point, whereas uniform continuity is a property of a function on an interval.
Well, this finishes our work with Unit 2, the derivatives. In our next TV lesson, we'll begin Unit 3 in a study of applications of the derivative. We'll see you then with Lesson 25.
Pre-recorded in the studios of the Maryland Center for Public Broadcasting.